In this video, we'll just be taking a little bit of time to introduce the inverse trigonometric functions. So with any operation that you've ever dealt with in math, addition, multiplication, squaring a number, you've eventually figured out what the inverse to that operation was, what the operation is that you would use to undo that operation. So to undo addition, we would subtract. To undo multiplication, divide. To undo that exponent of 2, we would take a square root, right? To undo squaring, we take a square root. So we also want to know how to undo the trigonometric functions. So if you look at this equation right here, sine of x is equal to this number. How do we figure out what the solution for x is? How do we isolate x? How do we undo this sine function? Well, the way that we're going to accomplish that goal is we're going to use what's known as the inverse sine function. So the inverse trigonometric functions undo the normal trigonometric functions. What you have to realize here is if you look at this equation right here, sine of x, what we put into a normal trig function, and sine is a normal trig function, is we put in an angle measure. So x is an angle measure. What we have this equal to, what's on the other side of this equation that you see on the screen, is the ratio for the sine function. Sine is opposite over hypotenuse. So if we took the opposite leg of the right triangle relative to the angle that's represented by x and divided by hypotenuse, we would have this as that ratio. So with a normal trig function, the input is an angle, the output is the appropriate ratio. Look at what I have up here denoted about the inverse trig functions. The input to an inverse trig function is actually a ratio, so we would put something like this into the inverse trig function, and what it's going to give us is it's going to give us the angle measure. So basically what changes when you go from an inverse trig function to a normal trig function or vice versa is the outputs and inputs exchange with each other. So if you look at this screen down here, I've done some of the steps. You see maybe for the first time Sine, and this looks like a negative first power. It's not. It's one of the common ways to represent the inverse sine function. Most calculators are going to use this notation here, sin, with, I'm not going to say to the negative first power. This is the inverse sine function. So when I apply inverse sine and sine, they undo each other, right? They cancel with each other, much like adding and subtracting the same value, multiplying and dividing by the same value, squaring something but then taking the square root of it. Those operations are all inverses of each other. They all undo each other. Same thing with the inverse sine and the sine. When you apply them together, like we see right here, they undo each other. We're just going to be left with x as the end result. And so look on this other side here. It says inverse sine of square root of 3 over 2. Now I'm going to talk you through a couple different ways to do this. If the calculator is in play, if your teacher, your professor, an SAT problem, the test you're taking, whatever it is, if you're able to use the calculator, you can break out the calculator. So I just have my TI-83 here. Now I am dealing with a situation where my class is measuring angles exclusively in degrees right now. So I'm in the mode menu, and I'm just going to change this mode to degrees. If you're dealing with radians, you can change it over to that and it'll give you the appropriate radian measure. But if I get out of this menu, and if you notice right above the sine key, you do see the same notation that we were looking at on the screen behind the calculator, actually to the side of the calculator right here. The inverse sine function is actually just above the sine button on the calculator. It's represented in yellow, so we have to hit the second button to access it. And all we're doing is we're literally typing in exactly what you see written right here. So inverse sine of square root of 3. And I don't want the 2 to be under the root, so I have to close my root and then divide by the 2, and then I can close that initial set of grouping symbols that it gave me. And you see that the answer that I get here is 60 degrees. Now, if you are dealing with a situation where your teacher, your professor is not allowing you to use the calculator, if they're asking you to use the unit circle, I want to talk you through how that can work as well. So that's what you see represented on the screen here already. So what I have is I have this numerator involving a square root of 3. If you think about the 30, 60, 90 ratio for right triangles, and there's another video where I mentioned some stuff about that, the 30, 60, 90 ratio is 1, 2 square root of 3. So I noticed that this numerator right here is a square root of 3. So if I'm trying to figure out what the inverse sine of square root of 3 over 2 is, I look at the numerator. It clues me in on the fact that I'm going to have to use a 30-60-90 ratio to build this answer. If I break out a unit circle, I draw a 30-60-90 triangle into the unit circle, I have to realize that I'm trying to figure out when sine is equal to that ratio. So when does sine of an angle equal square root of 3 over 2? So on the unit circle, the sine ratio corresponds to the y coordinate. So what that told me is that I wanted to draw a 30-60-90 triangle where my y value was slightly larger than my x value. Right, the unit circle is drawn in the coordinate plane here. So I have my x value across the bottom here slightly smaller than the y value that works up off of the x-axis. I did that because I saw this numerator, square root of 3, recognized that as one of my values from my base 30-60-90 ratio. I'm looking for sine of an angle to equal this value. So I'm trying to figure out what that angle has to be. I drew my y coordinate to be bigger than the x coordinate, and what that told me is that told me I'm going to have to open up with a larger angle here than I'm going to have opening downward up here within the first quadrant there. And if this is a 30-60-90 triangle, and I did the division by 2 to turn the hypotenuse of this triangle into a 1, right? If we're drawing a triangle into a unit circle, we need the hypotenuse to be a 1. So the reason why you don't just see 1, 2, square root of 3 as the sides of this triangle that I've drawn, I've already cut the hypotenuse down to what it needed to be. Since it's drawn into the unit circle, it had to be a 1. So that told me that my x coordinate was going to be the smallest value from the 1, 2 square root of 3 ratio, which is 1, divided by the same thing I had to take the hypotenuse down by to turn it into a 1. And then the middle side, the bigger leg, had to also be divided by 2 in order to keep everything proportional. You have to have some way of recognizing within the unit circle that you're going to be looking at a 60-degree angle in order for your y coordinate to be this positive value. So hopefully that made some sense. Just pay attention to what your teacher or professor is asking of you. Are you able to use the calculator? Do what I did a few minutes ago. Are you measuring angles in radian mode? You will all eventually be there if you're not doing that just yet. So you'll have to click your calculator over to that radian mode for measuring angles, or you can use the unit circle and give the appropriate value like we just did in this example. Last thing I want to say before we close out this video is a little bit about notation. So if you look at this screen, we've got the inverse trigonometric functions in this right-hand column, and we've got the trigonometric functions in this middle column. So notice the variables that are being used. The output, opposite divided by hypotenuse for sine of angle x is equal to y. The output for this cosine ratio, adjacent divided by hypotenuse, and then the input is the angle x. And then again, we see the variable y written right here. Tangent would be opposite divided by adjacent relative to the angle measuring x degrees or x radians. So the input in this column right here is x every single time. X is an angle measure. The output, y, is a ratio. Now look at over here on the inverse, in the inverse column. You see that the outputs and inputs have changed. So the fact that they're changing the variables or inverting the variables with each other is definitely not by accident. This is to show that when you go from a function to its inverse or vice versa, the outputs and the inputs are all going to exchange roles. So the output would be what you see represented as the variable x. This is an angle measure, angle measure, angle measure. This is a ratio. Y is ratio, ratio. We've already talked about the inverse sine function a little bit. We have the inverse cosine function to undo the cosine ratio, and then the inverse tangent function to undo the tangent ratio. Here's the thing I want to point out. You heard me say a little bit earlier within this video that this is not an exponent, this -1. It looks like where we would normally look to see an exponent on a trig function. When that exponent is a -1, let me step back and say this a little bit more clearly. In the spot where we would normally look for an exponent, when it's a -1 on a sine, a cosine, or a tangent, it does not represent an exponent. It represents the inverse. You saw my calculator. My calculator uses that exact same notation. Inverse sine, inverse cosine, inverse tangent above the sine, cosine, and tangent keys. So you are going to, if you're using your calculator, which I'm sure that at some point the majority of you will be doing it in some course, you're going to have to recognize these as the inverse trig functions. But because it's so easy to misinterpret what that -1 is and assume that it's an exponent, certain textbooks, certain teachers, professors are probably going to be using this notation as opposed to the notation that we've been using all along. Calculators are going to use what we've been talking about already, but you might see arcsine, arccosine, or arctangent. That's just a more clear way of representing inverse tangent, inverse cosine, or inverse sine. So just kind of pay attention to what your teacher, your professor is asking you to use for your notation, what your textbook uses, and act accordingly. When you see this sign, I'm going to say to the negative first power, but it's really not to the negative first power. That represents inverse sine. This is not cosine to the negative first power. It is inverse cosine, and that is inverse tangent. So it's not an exponent when it's a -1. It's an inverse of the appropriate trig function. Because that's easy to confuse with an exponent, the notation you see here, you might see the other notation being used. So in the next few videos, we'll do some more examples involving some inverse trig calculations. Eventually, we'll talk about what's known as a principal value. And hopefully by the end of this little sequence, we'll be pretty comfortable with what's going on with the inverse trig that we're introducing.